In the last tutorial session, we have seen this system of stochastic differential equations and then we have demonstrated that how the V, this second component, behaves over time, and then this system of equation actually is used for modeling asset prices, because this V stands for volatility fluctuations, which moves within some range, not a hard bound range, but there is a mean reverting dynamics of the process V, and then this S is model for asset price dynamics in financial market. Okay. Today we are going to see another stochastic differential equation, for which also we have some very nice geometrical pattern, okay, and for which we would be able to interpret that we can actually explain the pattern from the equation also. Okay. So, let us start that. So, this is Brownian bridge. So, what is Brownian bridge? So, for a pair of scalars A and B, let x, okay, which is a stochastic process defined for time only between 0 and 1, okay, be given by this equation. Okay. So, and then we would call that x is a Brownian bridge from A to B. Okay. So, what is the equation? Let us look at the equation more carefully. X t is defined as b plus 1 minus t times a minus b plus integration 0 to t 1 over 1 minus s dws, okay, where w is a Brownian motion. Okay. So, here let us understand that how does this process look like, okay, at the end points first. So, here t is running between 0 and 1. So, end points are time 0 and time 1. At time 0, we can put 0 here. So, if you place 0 here, this integration vanishes. On the other hand, here I would get 1 minus 0. So, that is 1 only. So, I would get a minus b here, but this would not be there. So, a minus b, but plus b already present here. So, b plus a minus b would give me a. That means, at time 0, x 0 is equal to a. Now, if we want to understand that how does it look at time t is equal to 1, then we have to place t is equal to 1 here. However, for this whatever it is, so t is equal to 1, but here t is equal to 1 makes everything 0, correct. 1 minus 1 would be 0. So, this part vanishes, this part would not be there, and we get b, correct. So, x t is equal to b, then x of 1. So, x 1 would be b. So, that means this process at time 0 is a, at time 1 it is at b, okay, and this process is called Brownian bridge between a and b. Why do you call it Brownian? Because it is coming from Brownian motion, okay, that is giving the randomness. And why is it bridge? Because it is bridging between these 2 points a and b. However, these 2 points could be the same points also, so it would be like bridge. Okay. Now, we would like to understand or derive what a stochastic differential equation for this process. So, this is the definition of the process, but we would see that we derive actually the stochastic differential equation for which this is a solution. Okay. So, here this is a comment that x naught is equal to a, x 1 is equal to b almost surely. So, this is called Brownian bridge from a to b. So, we would find SD representation, but that is very easy. So, what we do, we write down dxt here. So, differential we take from both sides. So, dxt is equal to, so this is constant, so it vanishes. I would get from here minus dt, and then this is product, correct. So, minus dt times this part, and 1 minus t times again the differential of this, that is 1 over 1 minus t dwt. So, that we write down here. So, first we write down this thing that it is 1 minus t times, so here 1 over 1 minus t dwt, and then minus sign here the whole thing a minus b plus integration 0 to t 1 over 1 minus this dws, and here from here minus dt. So, dt and minus sign is here. Okay, just taking differentials of both sides, I get this. Now, just simplification. So, here we can understand that this term can be rewritten as x t minus b minus 1 minus t. Okay, so that we do here. So, this a minus b, this thing is x t minus b divided by 1 minus t. So, x t minus b divided by 1 minus t, here minus sign is there. So, I get this b minus x t divided by 1 minus t. Okay. So, dwt, so from here we get dwt, here minus x t minus b divided by 1 minus t dt, and then adjusting the negative sign, we get this very nice equation, okay, very short equation, dxt is equal to b minus x t divided by 1 minus t dt dwt. So, in this equation we see two terms, and we relate that we also have obtained that, okay, one term is dt term and this dwt term, okay. So, in general ODE you just say that dx dt is equal to f of x comma t, okay, and then that denominator dt, if you write down, that means you want to see ODE as a integral equation, then you get dx is equal to f of x t dt, okay. But here you have extra additional term, this Brownian motion, that is giving you the randomness uncertainty, and that is why we are calling this stochastic differential equation, okay. So, here also we are getting that dxt is equal to b minus x t divided by 1 minus t dt plus dwt, okay. So, that is the equation, and where t is ranging from 0 to 1 and initial condition is a, okay. So, this is the SDE for Brownian bridge from A to B. Now, we are going to study few more other properties of Brownian bridge, okay. So, imagine that I have a Brownian bridge from A to B, where A and B are not equal. This B could be larger than A or could be smaller, okay. For without loss of generality, let us assume that it is larger than A. Then this x t, as it shows here, it is continuous because it is integration with this Brownian motion. That integral we have already seen that it is continuous martingale, correct. So, it is continuous and this is continuous. So, this is actually having continuous path almost surely. So, if the process moves from A to B, then any points between A and B, say for example C, should be touched by the process at some time tau, okay. So, now whatever the random time tau at which the process hits the level C, which is in between A and B. So, from that time onward, if I look at the process, okay, then this is like connecting C to B, okay. Is that a Brownian bridge? Answer is not pretty yes, because after all Brownian bridge by definition should be between time 0 to 1, here time is maybe smaller than 1, okay. So, one can ask that, okay, if I change time in an appropriate manner, so that after rescaling of the time I get from that point tau to 1 is like 0 to 1, I mean like 0 1 interval. If I do this mapping, after that mapping, can I make it a Brownian bridge? The answer is yes, we can do that. So, that is the thing I am showing it here. So, we do not need anything other than just manipulations, just calculus. So, I find that, okay, that is very interesting example for tutorial, that one would be confident that how these manipulations do happen, and whatever we have learnt earlier can be used here to achieve this, okay. So, before that, let us see bridges, this pattern and maybe simulation. If I have time, I would come back to the simulation, how to simulate. That means, how did I actually compute this particular realization of Brownian bridge. So, here this is a Brownian bridge from 0 to 1. So, A here is 0, B here is 1. Okay, and time is horizontal axis, and then this is actually simulated from the SDE, okay, the stochastic differential equation, whatever we have obtained from that we have simulated. One can actually simulate from the direct definition also, but here I have simulated from the SDE to check that how nicely it is coming. Okay. So, if I have time, I would come back to the simulation procedure also. Okay. So, let us go back to our question that from point C to B, okay, so at time tau, how or what is the appropriate time change so that the new process can also becomes under the new scaling becomes a Brownian bridge. Okay, so that was the question. So, assume that A is not equals to B and C is in between A and B. So, since Brownian bridge has continuous path, it hits at C at some point tau. Okay, so hitting time tau, which is of course between 0 and 1, almost surely it would hit here, and then we define yt. Okay, so this is doing step by step time change is equal to defined as x tau plus t. That means y0 is equal to x tau. Okay. So, y0 is equal to x tau, and then t is running between 0 to 1 minus tau. I cannot talk about t more than 1 minus tau because that is not defined, because when t is equal to 1 minus tau, I get x tau plus 1 minus tau, that is x1. Okay. X is not defined for time more than 1. Okay. So, anyway, time is here between 0 to 1 minus tau. Okay. So, that shows us the reason that we need to scale the time. Okay. The shifting does not help, the scaling is required. Okay, we do that. So, we define one Brownian motion w prime t, which is w t plus tau. Okay. So, it is just shifted process. So, from tau onward. So, here t is between 0 to 1 minus tau. Okay. And then here what we do, we take dyt is equal to b minus yt divided by 1 minus t. So, this yt as I have defined here would satisfy this SDE. So, this we can obtain directly from the SDE what we have obtained here. So, dxt is equal to b minus xt by 1 minus t dt plus dwt here. So, t plus tau is replaced by this thing yt, correct. So, if I replace t by t plus tau all the cases. So, here I would get 1 minus t minus tau, here I would get w t plus tau, okay, here also t plus tau, but x t plus tau is yt. So, that we are going to use. So, you would get that 1 minus t minus tau and d and w t plus tau is w prime t. So, d w prime t, and here in the numerator you would get b minus x t plus tau, but x t plus tau is yt. So, you would get in the numerator b minus yt. So, we get this new SDE for for this process y, where y0 is equal to x tau, because it is 0 x tau, and x tau is c by definition of tau, and then y1 minus tau is x1 because 1 minus tau here is x1 and x1 is b by definition of x. Okay. So, we know pretty sure that we understand now y is just starting at time 0 at c, and at 1 minus tau which is a random time, there it is touching b, but still is random, correct. So, it is not exactly like a Brownian bridge, you have to do something more. Okay, the something more comes here. So, this is our proposal that let us define a process, new process z. So, z of t prime, where t prime is between 0 and 1, z of t prime is defined as this fraction plus c plus b minus c times t prime. This fraction in the numerator we have y t prime 1 minus tau. See here that earlier the time interval on which y is defined has the length 1 minus tau, that is possibly less than 1. Okay. So, but t prime is between 0 to 1. So, what we are doing is the t prime into 1 minus tau we are taking. So, when t prime is 0, this is y 0. When t prime is 1, this this time would be 1 minus tau. So, the whole process y that is scaled into this. However, we also need to adjust this a little more. So, y t prime into 1 minus tau minus b plus b minus c times 1 minus t prime divided by square root of 1 minus tau. Okay. So, this depends on tau, of course, I mean that is expected. So, here tau appears plus c plus b minus c t prime. Okay. It looks a little complicated, but it is not that complicated actually. This is the natural thing to do actually, because I would like to match it at time 1 to b. So, I have subtracted here and then later I have added also, okay, because when t prime is equal to 1 you will get b there from that. Okay. So, let us just analyze what did we obtain here. So, put t prime is equal to 0 both sides, I got z0. So, z0 is equal to y0 minus b plus b minus c. So, this b and this minus b would cancel. So, I would get y0 minus c. Okay. y0 is anyway c. So, y0 minus c is 0. So, numerator is 0. Okay. On the right hand side I have here I have get t prime is equal to 0, that this factor would vanish. So, I would get c. So, z0 is equal to c. Now, we see from this definition what is z1. Okay. So, we would put t prime is equal to 1 here. If we put, then I would get y of 1 minus tau, that is b anyway. Okay. So, b minus b, that is 0, and then t prime is equal to 1. So, 1 minus 1 is 0. So, numerator is 0, and then here t prime is equal to 1 if I put, then I would get b minus c, but this c and this minus c would cancel each other. So, I would get b. So, z of 1 is b. So, z is connecting c to b during the time interval 0 to 1. Okay. So, surely this is a very nice candidate for Brownian bridge, okay. But any process which connects the 2 points at time 0 and 1 is need not be a Brownian bridge. I mean, it should have the similar statistical property also. So, that is the thing we need to check, okay, and that is the thing for that we actually have appropriately chosen that denominator. Okay. So, let us see that. So, to prove that this process Z is indeed a Brownian bridge from C to B, what are you going to do? We are going to show that this Z satisfies the stochastic differential equation. Okay. So, that stochastic differential equation, I mean this characterization we have already obtained, that if a process satisfies this SD, then it is a bridge between A to B. A appears here, B appears here. Okay. So, this is the characterization we would consider, and then okay. So, now for proving that we need a little more. So, we define another Brownian motion W double prime. So, that is defined as W double prime at t prime is defined as 1 over square root 1 minus tau W prime of 1 minus tau times t prime. Okay. So, here this, why is it a Brownian motion? I mean that is subject to proof. We are going to prove that, but before that let us see that what happens, that here I have changed the time since tau is less than 1. So, 1 minus is smaller than 1. So, this process runs little slowly. Okay. However, we also divided by square root of 1 minus tau a smaller number. So, that means we have actually scaled up, I mean this fraction is more than 1. Okay. So, to prove that this is a Brownian motion, what we are going to do is that first we check whether it is a continuous process. Yes, it is a continuous process, the way it is defined, since W prime is continuous, this is continuous, and next is that what is this quadratic variation. So, then we are using Levy's characterization of Brownian motion, that if the quadratic variation is identity function, then it is a Brownian motion. So, d W double prime t prime. So, that we obtain, as we have seen in the last tutorial session, that to compute it we are going to just take the corresponding different square of the differentials for computation. So, here 1 over square root of 1 minus tau, and here the differential is d W prime 1 minus tau t prime and the whole square. So, then from here this part I would get 1 over 1 minus tau the square of the square root is 1 over 1 minus tau, and for this the quadratic variation of w prime appears, and that would be exactly, since this is Brownian motion, it will be 1 minus tau times t prime, okay, dt prime, and this 1 minus tau what would appear, and here in the denominator also you have 1 minus tau, they would cancel each other, and what would remain is just dt prime. So, that justifies that the double prime defined this way is also a Brownian motion. Okay, so, this is something we are going to use to obtain an SDE for the process Z. Okay. So, this is the way we do. So, here we show that Z is a Brownian bridge from C to B. So, we show that Z satisfied dz t prime is equal to B minus z t prime divided by 1 minus t prime dt prime plus d w double prime t prime, and z0 is equal to C. So, this thing, okay, I am going to explain it. First I see that let us look at the result. End result is that Z satisfies this SDE. So, from definition, not only definition, after the definition we derived, that is a characterization of the Brownian bridge using stochastic differential equation. So, there what we have seen is that if some process satisfies this equation, then we say that this is a Brownian bridge. Okay, the continuous solution of this equation would be the Brownian bridge, and is starting from C to B. Okay, the bridge from C to B. Okay, so the proof starts here, that we are having z t prime is equal to this thing, and we take the differential of both sides. So, when we take the differentials, this would not appear here, but dy would appear here. From here minus dt prime times b minus c would appear here. From here dt prime b minus c would appear. Okay, so b minus c dt prime appear from that side, and here dy t prime etc., and minus b minus c dt prime. Okay, so I have from here there I have obtained this equation. Now, from here we do more analysis here. So, what we do is that we use the formula for SDE for y. So, y itself satisfies one SDE that we have written here. So, we substitute that part. So, here what dyt we have, we substitute this by the part on the right hand side. However, here it is written in terms of t, but there it is different time. So, that we have to appropriately change. Okay. So, here you have t prime into 1 minus tau. So, here everywhere wherever I see t, I should write down there t prime into 1 minus tau, t prime into 1 minus tau, etc. Okay. So, here w prime t prime into 1 minus tau, that I need to write down here. So, that I do here. So, b minus y t prime into 1 minus tau, and here 1 minus t was there. So, I am writing 1 minus t prime into 1 minus tau here, and then so dt, instead of dt I should write 1 minus tau dt prime. Okay, and here so these things, and from Brownian motion part I should write d w prime 1 minus tau t prime. Okay, so these are the things we just do, and then this b minus c dt prime I just have written here. Okay, sounds good. Now, next I need to simplify this. Okay. So, first simplification is that we use the definition of w double prime, that w prime 1 minus tau t prime is w double prime. Okay, so 1 over, I mean this fraction is also there, this is w double prime. So, that we use here 1 over square root of 1 minus tau is already present, and this part is there. So, this together would give me dw double prime t prime. Okay, from here I am going to get it. And so, from here this side what we are going to get is b minus y t prime 1 minus tau. See, here a very nice thing has happened, because 1 minus tau and here minus t prime 1 minus tau. So, I can take 1 minus tau common. If I take 1 minus tau common, then it will be 1 minus tau into 1 minus t prime. So, 1 minus t prime stays here, and that 1 minus tau cancels with this 1 minus tau. So, after this simplification I would get b minus y t prime 1 minus tau divided by 1 minus t prime. Okay, and here minus b minus c. Okay, so dt prime. Okay, and then this part I have already explained. This term is this term. Okay, as before. Okay, so now we back substitute the z, okay, because for z we have one equation. Okay. So, this is a formula for z in terms of y. So, here in the denominator I have 1 over square root of 1 minus tau, and numerator we have this y term minus b plus b minus c times 1 minus t prime. So, these are things, but here when we actually write down this also in the numerator, I would get b minus c into 1 minus t prime, as it appears here. So, this would appear on in the numerator because 1 minus t prime is here, correct. If I put it in above, I would get that, and then this y and minus b also is here. So, only the sign is negative. Okay. Here I had plus b minus c into 1 minus t prime, here we had minus b minus c into 1 minus t prime, and only the sign is negative. So, I would get minus z t prime from there. Okay. But there are some other terms, this term. So, this term would go here. So, minus z t prime plus c plus b minus c t prime. Okay. So, plus c plus b minus c t prime. Okay. From here we are getting this numerator. However, in the denominator we have 1 minus t prime. Okay. And this square root of 1 minus tau would not appear because that was also already there, correct. We have taken care. Okay. So, only 1 minus t prime would remain here, and numerator would be this, and dt prime as it is, and this part was as before. Okay. I am just rewriting this thing. Okay. Now, here it is just a matter of manipulation, because here we have b minus c dt prime, okay, and then if I put it together, so we take dt prime common, then I would get b minus c into 1 minus t prime from there also. So, with the plus sign here, b minus c into 1 minus t prime, but minus sign is there. So, minus t prime into this thing would cancel with this. Okay. So, what would get that plus b minus c would appear here, but c plus c is here. So, this plus c and that minus c would cancel. So, I would get only b here. So, my b minus z t prime would remain in the numerator, and denominator is 1 minus t prime dt prime, and I would have only this more term dw double prime t prime. Okay. So, by this we have finished the proof that the z satisfies this stochastic differential equation, and therefore, z is a Brownian bridge from C to B. Okay. Thank you.